Hello once again, and yet another video on the application of the Laplace transform to circuits. This time we'll look at an impulse response of an LC circuit, a second order circuit, and let's get started. So the input to this series LC circuit is our usual delta function. So it basically has same kind of deal as before. It's located at t equals 0 and has an area of A. Units are volt seconds. So if you haven't watched the previous two videos, please do so. That'll give you a heads up on some of the things that I won't be going into as much detail as I did in those videos. So once I have this, right, once I have the circuit, I want to solve for example, the inductor current, the capacitor voltage, the state variables. I go ahead and apply the Laplace transform to the entire circuit. So that will result in a simple circuit that looks like this. Inductor here, capacitor, the value of the source is simply A, impedance is SL, this impedance is 1 over SC, and of course the variables of interest, in this case at least the primary variables of interest, are going to be inductor current and the capacitor voltage. So now once we have the circuit, we can just go apply what we know. Once again, this circuit is assuming zero initial conditions. So both the inductor current and capacitor voltage are going to start from zero initial conditions. But because we have an impulse, the voltage and or the current may jump instantaneously. Actually, at least one of them will jump instantaneously. And we'll see that. Now, since this is a series circuit, it's typically easier to start with the series current first. So the series current in the circuit is the inductor current. So let's just do that. Let's just solve for the inductor current. And you can do that with Ohm's law. So with Ohm's law, we have that the inductor current, ILS, is the applied voltage, which is in this case A, divided by the sum of the impedances. That's all there is to it. So once we have that, now we start the simplification process. For example, first thing to do is maybe multiply top and bottom by SC. That'll get rid of the fraction in the denominator. So we have A times S times C divided by S squared LC plus 1. And now we're going to divide top and bottom by LC. And the reason we're doing that is because the form of the expression that we have that involves a quadratic for second order systems, for Laplace transforms, has the highest order term, the polynomial equal to 1. So we like to have the S squared term have a coefficient of 1. So if we divide top and bottom by LC, this is what we get. We get A over L times S divided by S squared plus 1 over LC. And now, this is in a standard form actually of something that we see in the table, in the Laplace transform table, the Laplace transform pair table. So let me write it this way, and you'll see why in a second. So A over L times S divided by S squared plus, and the 1 over LC, I'm going to write it this way, 1 over root LC squared. So I really haven't changed anything there. I just kind of formulate it this way. And the reason is because one of the Laplace transform pairs is the following. When you have something like S divided by s squared plus omega naught squared. This happens to be associated with cosine omega naught t ut, where we can identify, in our case at least, that omega naught is 1 over root LC. So this comes up so often that it has a name. This is called the resonant frequency. Resonant frequency. So for our case, since this is our ILS, then our ILT, sorry, this is just the Laplace transform, right? It's just the inverse Laplace transform operation. So what this means is that ILT is simply going to be a cosine. And of course, we're going to have a factor of A over L out front. So this is going to be ILT equals A over L cosine of omega naught t times ut, where omega naught is defined as 1 over root LC. If you want, we can leave the 1 over root LC in there. 1 over root LC times t would be the argument of the cosine. Now, we've seen before that A over L has the units of amps, actually. So I won't go over that again, but if you want to go ahead and go back to the videos and take a look, what you will see is what we did is we basically said that we know that as far as units are concerned, VL is L DIL dt, and so the units that we have for something like this are volts, henries, right, and then you have amps divided by seconds. So if you cross multiply, you'll see that if you have volts times seconds over henries, right, is equal to amps. And that's exactly what we have in A over L. It's a maybe bad choice of variables there, but A stands for the area, right? That's volts times seconds. That's from V of T. Whereas L is Henry, so volts seconds over henries is amps. So the units here are amperes or amps, right? So that's true. And if we have to sketch this, we can just simply sketch it like this. So here's time, right? And it's a sinusoid, but it's equal to 0, right? Before t equals, so let me just mark t equals 0 here. Before the impulse occurs at t equals 0, it's sitting at 0, and then it becomes a cosine. So actually it jumps like this, and then it's going to oscillate. So the key point here is that this is ILT, right? IL of 0 minus is 0 amps. That's given. But IL at 0 plus, that's equal to A over L, right? So this thing oscillates. And of course, one period, right, of this oscillation, which goes from this is 0 and this is one period, let's call it T0. T0 it's 2 pi over omega 0. Right, so it's actually 2 pi root LC, because omega 0 is 1 over root LC. So that's the period, and this will oscillate forever. It's a harmonic oscillator. So the current just keeps oscillating this way. So when the impulse comes, it just kind of sets this oscillation going, and this thing oscillates forever basically. Because there's no resistance, the input doesn't decay. It doesn't grow, but it doesn't decay. It just sustains oscillations. Everlasting sinusoid. Okay, that's ILS. How do we find, for example, the capacitor voltage? Well, the same current ILS that's going to the inductor also goes through the capacitor because it's a series current. And so we can just use Ohm's law. VC is equal to the impedance of the capacitor times IL. Let's just write that down. Right? We have VC of S equals 1 over SC times IL of S. I mean, this is Ohm's law. It's Ohm's law. And IL of S, we know already. We can use any of the expressions that we develop. Maybe we'll use this one right here. So let's just copy it. I won't even have to write it down. So copy, and we'll just move it down here. We'll paste it. Here it is. All I gotta do is I just gotta multiply this by 1 over SC. So this equals, right, 1 over SC times the expression that I just pulled in. That's ILS. So what happens here? Well, the S's cancel. So this S cancels with this S. And now I have a constant, right? Let's just write what it is. So I have something that looks like this. I have the denominator, which looks like S squared plus, 1 over root LC squared. And in the numerator, I have A over LC. Okay, so what does that look like? Well, this is there's another term in the table which corresponds to a sinusoid, just a sine wave, not a cosine, but a sine. And it looks like this. So it has the form of omega naught divided by S squared plus omega naught squared. If you're not sure about it, you can just look it up. Look at the first lecture in the series, or you can look at any tables. But this would be something like sine omega naught t ut. Omega naught as defined before, just to remind you, omega naught is defined as 1 over root LC. It's just a shortcut, you could say, definition. So here we have the denominator S squared plus omega naught squared, but in the numerator we have A over LC. So that's A times omega naught squared. So here's what we're going to do. We're going to write it this way. We're going to write this as A over root LC times 1 over root LC times S squared plus 1 over root LC squared. I mean, if you want to write this in terms of omega naughts, right, what we really have up here, if you have to be kind of simplified about it, what we have up there is A omega naught squared divided by S squared plus omega naught squared. So if you pull out one of the omega naughts, what you have is you have A omega naught times omega naught divided by S squared plus omega naught squared. Okay, of course, this portion right here in the parentheses, that's just a sine wave. That's just a sine. It's sine omega naught t ut. And A omega naught is a constant. So what that means is, if I have to write VC of S again here, so VC of S is A omega naught times omega naught over S squared plus omega naught squared. And if you do the inverse Laplace transform of this, you get Vc of t is equal to a omega naught sine omega naught t u of t. That's what we get. And that's the voltage. So we can sketch this as well, right? If we sketch this, I mean, it'll be a sinusoid again. It'll be a sine wave, though. Won't be a cosine. And so, you know, it'll be something like this, right? Here's, let's say here's 0. Here's time, t. And of course, these circuits are all starting from zero initial conditions, like that. And that's going to be a sine wave, so it's going to go like this, right? It's just going to keep oscillating. Doesn't decay, doesn't grow. And the amplitude here is a omega naught. And of course, on the bottom, you have minus a omega naught, but that's how it looks like. And one period, right, from 0 to here is one period, like this. And t0 is the same as before. T0 is 2 pi over omega naught, which is 2 pi root LC. That's how it looks like. And what you see from here is that in this case, the initial condition, Vc0 minus, obviously is 0. So Vc0 minus is equal to 0 volts. Vc0 plus is also 0 volts, because if you plug in t equals 0 into this function, sine of 0 is 0, so you get 0. So the capacitor voltage is actually continuous. So it turns out that Vc0 plus is 0 volts. So in the impulse response of the series LC circuit, capacitor voltage is continuous. Inductor current is not. Inductor current jumped. You can see how it jumped from 0 to A over L. And A over L is a current, right? By the way, is this term here, is that a voltage? Because I just marked the amplitude as A omega naught. I didn't say anything about it. But is that voltage? It is. And the reason is because, remember, A is an area. It's volts times seconds. So if you think about A omega naught, what is that in terms of units? So you have volts times seconds. And omega naught is radians per second, right? So as far as units, it's per second. Radians is just a number. It's not a unit, right? So this, in fact, is volts. So that's true. It's definitely volts. And is what we get. So it's very interesting that you have a circuit like this, no resistors, right? And you go and you hit it with an impulse. And you have to understand what the impulse is doing, right? So at t equals 0 minus, it's not there. At t equals 0 plus, it's not there either. Basically, this voltage source is a short circuit. It's a short circuit for before 0 minus and after 0 plus. So all it does is it kind of kicks the circuit, literally kicks the circuit and just goes away. And then the LC circuit oscillates, right? It's just going, energy is going back and forth between the inductor and the capacitor, but it never dissipates. There's no place for it to dissipate. There's no resistors. So it oscillates forever. So this is basically a harmonic oscillator. It's like a mass spring system with no friction, right? You hit the mass, you poke the mass, and you let it go. It just goes up and down, but it never dissipates. It just keeps doing the same thing over and over and over again without any change. Just oscillates forever. So this is actually a good example to know, and you can see that the we have also these two new Laplace transform pairs that we use that we never used before. It's the cosine and the sine. So these are the solutions. Okay, So maybe we can also think about what would happen with a parallel circuit, right? Maybe I won't go through this whole thing, but you might ask the question: suppose you have a parallel circuit. Maybe you have a parallel LC circuit. How would you do that problem? Let me at least set it up. Okay, so the question is this: suppose I have a current source. And I have a inductor and a capacitor. It's still an LC circuit. No losses. So here's the L, here's the C. And the current source, IST, let me write it this way. It's equal to Q times delta T. Now, why am I writing it as Q? Because remember, the thing that multiplies the delta T models what? Models the area, right? Area under the current versus time curve or function. So really, the units of Q are amps times seconds, which is charge, and therefore it makes sense maybe to mark it as Q. It makes sense that way, at least to me. So here we have the inductor current with the capacitor voltage. And let's say the initial conditions are 0 again. So we have VC 0 minus is equal to 0 volts, and IL 0 minus is equal to 0 amps. So they're both starting from 0 initial conditions. What would you do here? Well, let me just start it off, right? What you would do is you would go to the equivalent circuit, the impedance circuit. Here we go. And this is the current, ILOS. Here's the voltage, VC of S. So the typical thing to do is find the inductor current capacitor voltage. How do we do that? Well, I mean, you can have your choice, but in a parallel circuit, typically we go for the capacitor voltage first. So maybe that's what we should do. How do we do that? I mean, there's many ways you can do it, but I would just write a KCL equation maybe, right? Because I know that VCS is the voltage across both the inductor and the capacitor. So I would say, right, you could say, for example, that current coming in is Q and current leaving is what? Well, there's VCS over SL plus there's VCS over 1 over SC, right? So this is a KCL equation written at the top node right here. So current that comes in is Q. The current that leaves is V over Z, like V over R, right? For both of the elements, right? So both the inductor and the capacitor have VC across them. That's the common. So maybe this is a, relatively simple thing to do. And this will give you an equation for VC of S. Now, after you've written this, it's just a matter of how you want to manipulate this, right? So maybe you want to write something like this, right? Maybe you want to say Q equals 1 over SL plus 1 over 1 over SC, which is just SC, times VC of S. And so VC of S is what? Well, VC of S is equal to Q, right? Divided by that term in the parentheses, which is SC plus 1 over SL. Okay. What do I do now? Well, just a manipulation. Again, it's straightforward. Let's see where it gets us. So what we do is we'll do multiply top and bottom by SL. So we have SL times Q divided by S squared LC plus 1. You see that term appearing again. Divide top and bottom by LC. Now we have something like this. We have so we have S squared plus 1 over LC. And the numerator, of course, divided by LC, you get S over C times Q. So Q over C times S, you could say, right? Because we divide by LC. Now, this should already start making sense to you, because if you look at Q over C, what's Q over C? That's volts, right? Because charge is equal to volts times capacitance. So Q over C has the units of volts. And this makes perfect sense because you have Q over C times S divided by S squared plus omega naught squared. Right? Omega naught, again, by definition, 1 over root LC. It appears in so many places, as I said. You write it this way. And now you can see, so let me just write this one more time again down here. So VC of S is equal to Q over C, right, times what? I'm just writing it over again. VC of T is going to be a cosine. Inverse Laplace transform. VCT is Q over C times cosine omega naught T UT. So you can see right away that the capacitor voltage will jump in this case, as opposed to the previous case where the capacitor voltage was continuous. And you can tell that because you can look, this is a cosine, right? So it's a cosine. It's going to be like this, right? It's going to jump. Well, I mean, the jump kind of, not straight up, but it does this, right? And this peak value here is Q over C. And of course, minus Q over C on the bottom. But the point is that VC0 plus is Q over C, right? VC0 plus is Q over C. And of course, VC0 minus is 0 volts. So the capacitor voltage did jump. And Q over C is indeed volts. Right? We know Q is C times V. I mean, if you don't believe that, you know that Q is definitely amps times seconds, where capacitance is farads. So the question is that volts? Is amps over seconds divided by farads, is that volts? Well, we can use a similar trick as we did before. I know that IC is C dVC dt. Okay, and what are units of this? Well, you have IC is that I is amps, right? And then C is farads, and VC is volts. Okay, and time of it's seconds, right? So you can see from here, if you cross multiply, that if you do amp seconds, right, cross multiply by seconds divided by farads, so you know that amp times seconds over farads is indeed volts. And that's exactly what we have over here. Amp seconds over farads. That is volts. And of course, you can find the inductor current by just doing VC over SL. We know VC, divide by SL, do another Laplace transform inversion. And you'll find that that's going to be a sine. I'll leave that to you. But for now, that's all I wanted to say. Until next time.